Are there any questions from last time's lecture? Okay, so if not, I'm going to start the lecture. Can you see the screen?
Yes, sir.
Yes, sir.
Okay, thank you. Okay, so if you recall last time, there are some questions which several of you asked about how we can deal with complex variables, okay, because the Lagrangian that we had written down was complex, okay, and we are dealing with the independent variables psi and psi star, which are themselves complex. So what I thought I'll do today is to describe in detail how it can be done with real variables, but I'll do it only once. Later on, we'll have to use this kind of, we'll encounter this kind of situation several times, in particular while quantizing Dirac equation. At that time, I'll proceed by assuming that the field and its complex conjugate are independent variables. But if you have any doubts there, you have to go back to what I'm going to do today and see how it can be done also with real variables. So today, the goal will be to try to understand whatever we did last time, quantization of the field in terms of real variables. So for this, we'll start with a slightly different looking Lagrangian, where we have transferred earlier Lagrangian had just I h bar psi star del psi del t. We have put a half here, and then you have added another term, which is minus half I h bar del psi star del t times psi. You notice that if we construct the action, but we also integrate over time, then up to total time derivative, these two give the same action, because you can just integrate by parts this and get back to the original Lagrangian that we had. Yes, this minus half will become plus half, and the time derivative will get transferred to psi. Okay. Of course, we have boundary terms, but because the boundary terms are not varied in the action principle anyway, it will not matter that you have extra boundary terms in the new action. So let's start with this Lagrangian and see how we can quantize it by following standard procedure with real variables. So for this, let's again suppose that UN form a complete basis of functions, and then we expand the field psi in this expansion. Because psi was a complex, A and T's are also complex. But let's just proceed anyway. Okay, we are not quantizing as yet. So as we have seen earlier, okay, in a slightly different context, that if we now substitute this in this Lagrangian and use the fact that the UNs are orthonormal, you will get a Lagrangian of this form. Again, this is very similar to the Lagrangian that we had last time, except that this half was not there and this term was not there. And you can see that this Lagrangian and the earlier Lagrangian are again related by total time derivative, which does not affect the equations of motion. So now we are going to make a departure from what we did last time. Are there questions? Okay, so you are going to make a departure from what we did last time. And instead of trying to quantize in terms of ANs directly, or instead of trying to define the canonically conjugate momenta of the ANs, we will first write AN as its real part, Bn of t and ICN of t, and think of Bn and Cn are independent dynamical variables which are both real. If you substitute this into the action, you will get a Lagrangian which has this form. This requires a little algebra, but it's not hard. In particular, the Bn terms, okay, will cancel between these two. And similarly, the Cn terms will cancel between these two. only the B and Cn cross terms will not cancel, because here you will get a conjugation will bring an extra minus sign, and then this minus sign over here will compensate for it. So if you just substitute this here, and if you evaluate what the Lagrangian becomes, you will find that the Lagrangian in terms of Bn plus Cn becomes this.
Sir?
Yes?
Sir, I think there is a typo. You have conjugated twice. The dn.
Yes, thank you.
Yeah.
Okay. So this should be not conjugated, this is just an of t.
Yeah.
Okay, it's dan star dt times an of t. Thank you. Okay, and this is, you see from here that this an should come from the side over here. Okay, any other question, comments? Is everything okay so far? Pritam, is it okay?
Yes, sir.
Okay, Manojit?
Yes, sir.
Okay.
Sir,
Yes, go ahead.
sir, which quantity is real now?
Cns and Cns are real. Okay? And the Lagrangian
Yeah.
is a manifest.
Sorry?
The Lagrangian is real.
Okay.
There's no I over here, right? See, that you can see from here. If you, I perhaps didn't say it. If you take the complex conjugate of the first term, right, what will happen? This I will change to minus I.
Yeah.
I star will change to psi, this here.
Okay.
And this will change to del psi star del.
Oh, right.
So the second term is the complex conjugate of the first term.
Yeah.
That's why this Lagrangian to begin with is real.
Right.
And you also see it here. You want to write in terms of the components. Here Bn's and Cn's are manifestly real, right? Because Bn is defined as a real part of N and Cn is defined as the imaginary part of N. So Bn and Cn are manifestly real. And when you substitute here, you see indeed that the Lagrangian is manifestly real.
Right. Thank you.
Okay, so here is the Lagrangian again. So now we are going to check that the equations of motion that we get from this Lagrangian give us the correct equations of motion. This of course we expect, because after all, as we argued that this Lagrangian corresponds to the same action up to total derivative. But let's check this anyway. So the equation of motion for Bn is d dt of del L del Bn dot minus del L del Bn equal to 0, and similarly the equation of motion for Cn. Now when you compute this, you get h bar times Cn. Okay, so that gives you a term h bar dC and dt. When you calculate this, you get contribution from two terms. First of all, here is a Bn. So you will get minus h bar dC and dt. So that gives you another factor of h bar dC and dt. And then you have to take the derivative of this. That gives you minus 2 E and Bn. So that combined with this minus sign gives you plus 2n. So this is the equation of motion that you get by varying with respect to Pn. Similarly, when you vary with respect to Cn, when you get the equation of motion for Cn, this gets contribution from here. This is the only term that contains Cn dot. So that gives you minus h bar dBn dt. And then this has two contributions. One from here, that gives you minus h bar dBn dt, and then the other term is from here. So these are the equations of motion. Okay, of course, you can cancel the factor of 2 clearly, right? Because this gives you 2 h bar dC and dt plus 2 E and Bn. So factors of 2 can be cancelled from here as well as here. And now you see that if we take the first equation plus I times the second equation and use the fact that An is Bn plus ICN, you get back the equation for An that we had encountered earlier. Let's see if that is the case. So let's look at the time derivative part. So first gives you Cn minus IBn, d dt of Cn minus IBn. So you can take a factor of minus I outside and you will get minus IH bar times d and dt. Here you get 2En times Bn plus ICN, that's En times n, right? 2 has been cancelled. And this in turn gives us back the Schrodinger equation that we want to study, namely I h bar del psi del t minus h hat psi. So this verifies that the Lagrangian that we started with does give the correct equations of motion. Okay, are there questions?
Sir,
Yes.
sir, instead of writing an is equal to bn plus icn, we could have just proceeded with an, keeping an itself. Then also we will get the same
Yes, we
equation.
could. But since last time there are people had some doubts about whether varying with respect to complex quantities is okay, right? Because the Lagrangian.
Okay.
That's why I thought that I'll do it everything in terms of real time. But as I said, this is I'm doing it once and for all. Okay. Then later on, when you encounter situations like this, we'll think of the field and its complex conjugate as independent variables. Okay, but today we want to do everything in terms of real variables. But you are right that we could have varied with respect to n and gotten the equation, this equation directly. Are there questions? Priya, is it okay? Priya Ghosh?
Yes, sir. Yes, sir.
Okay, thank you. Okay, so now we have to proceed to quantize it. So for this, I have written down the Lagrangian again. And let's try to see what we can do with this Lagrangian. So the first thing is to write down the canonically conjugate momentum. Because one's normal procedure for quantization is that you first define the canonically conjugate momenta, write the Hamiltonian in terms of the coordinates and momenta, and then quantize by replacing the Poisson brackets by 1 over I h bar times commutator bracket. Okay, but let's see what happens here. So if we define the momenta that are conjugate to the coordinates, then Bn tilde, this is a momentum conjugate to Bn, is given by the derivative of L with respect to Bn dot. And you can see from here that that gives you h bar times Cn. Cn tilde, which is a momentum conjugate to Cn, is by a similar exercise gives you minus h bar times Bn. And now the Hamiltonian you can easily construct. Okay, this is the definition of the Hamiltonian. And you can see that when you substitute for B tilde n in terms of Cn, or vice versa, when you substitute C tilde Cn in terms of B tilde n, what you'll find is that this vanishes identical. Okay, let me put it again. You can either substitute B tilde n in terms of Cn and combine with this, or here we have Cn, we write in terms of B tilde n. The main point is that these two terms in L cancel with these two terms here, and what we are left with is this last term, which is sum over n En times Bn square plus Cn square. And now if we rewrite it in terms of the A's, we see that indeed we get back what we had earlier, En times An star An, right? Because An is Bn plus Icn. Is this okay so far? Okay, so let me proceed. So now we come to the main confusing part. So you have to understand how to quantize a system. And the problem of quantizing the system, okay, which we had also encountered in a milder form last time, is that the momentum variables, unlike in normal systems where the momentum is given in terms of the velocities, and we eliminate the velocity in terms of momentum, here the momentum is given in terms of the coordinates themselves. Okay, because Bn's and Cn's you think of as generalized coordinates, B tilde and C tilde n are the generalized momenta. So the momentum and coordinates are not independent, which basically means that this is a constraint system. Whenever momentum and coordinates are not independent, we call it a constraint system. So you have B tilde n equal to h bar Cn, C tilde n equal to minus h bar Bn, And now you have to understand how to quantize this constraint system. Now one might take a naive approach and say that let's take Bn and Cn as independent variables, right? Because after all, B tilde n and C tilde n are given in terms of Bn and Cn. And now from here we see that Cn is given by B tilde n by H bar. So why not use the fact that the commutator between Bm and B tilde n is supposed to be I H bar delta Mn when you quantize, and write B tilde n as Cn times H bar to get an equation of this form. Okay? Bm times Cn, okay, just substituting B tilde n as Cn times H bar from here, we get Bm Cn commutator is this, which is I delta n. Is this clear? So all you are saying is that Bm, to calculate the Bm Cn commutator, I can substitute Cn equal to B tilde n by H bar. Then you use the fact that Bm B tilde n is I H bar delta Mn, and then 1 over H bar cancels this H bar, and you get I delta M. However, it turns out that this is the wrong answer. And we'll eventually find the right answer. But the reason that this is wrong is because this makes use of only one of the two constraints. Right? We use this part of the constraint, right? I think Cn is equal to B tilde n by H bar. But there's another constant which you forgot. So to really correctly quantize this system, we have to take into account both constraints simultaneously. Fortunately, last time when we are using complex variables, the constraints are simple enough. They are not coupled constraints of this kind, so that we could eliminate one set of variables in terms of the other and get the result without too much trouble. But now we really have to deal with the both constraints together, and this is what we have to learn: how to take into account the both constraints together. And for this, we have to this time really go through Dirac procedure for quantizing constraint systems. So what I'll do in the next few slides is to review the procedure. I'll not say how it came, but I'll just state the operational procedure for quantizing constraint systems of this kind. Are there questions?
Sir, even here, if you go to the expression for Lagrangian in which you have written it in terms of B and C.
Yes.
Yeah, here. If you do a partial integration in the second term,
Yes.
then it again becomes Cn Cn d dt of Bn, and the first term becomes twice Cn d dt of Bn.
Yes.
So, like, can we do that here again? And the constraint that we'll get from on the momenta would be the conjugate momenta of Cn is 0 and that of Bn is Cn.
Yeah, in fact, 2Cn.
2Cn, yeah.
Yeah, exactly. Okay, so we could do that here, right? But this may not be possible in general, and the question would be, right, that suppose you get some answer by doing this.
Yeah.
Right? How do you know that that answer is right and not what you are getting from here?
Okay.
Okay. So the point is that once it's good to go through the full procedure. See, the whole idea of this Dirac procedure for quantizing the constant system is that this doesn't depend on which variables you choose to quantize eventually, right? Or how you do it, whether you add total derivatives to Lagrangian or not. The result is independent of how you proceed, how you do the quantization. Okay. So once we understand this procedure, then we can apply it either to this form of the Lagrangian or what you are suggesting. We take the total derivative out and write this as Bn times dC and dt and quantize it from there.
Okay. Fine.
But we want to see what is the general procedure.
Okay.
Because while this may work in this case, it will not always work. Okay, and in fact, we will encounter situations in quantum field theories where you really have to go through Dirac's procedure for quantizing it.
Okay.
Is this okay?
Yes,
Okay,
sir.
so afterwards we can come back to this and check that if you do what you are suggesting, by integrating by parts whether you get the same answer or not. Okay, and in that case, as you said, the constants will be simple enough so that you will get the right answer by doing this.
Okay.
Okay, other questions?
So
Yes, go ahead, please.
regarding the other constraint that we had on Cn tilde,
Yes,
that is simply minus h cross bn. So that is also satisfied by this commutative bracket, isn't it?
that is
If
true.
we dictate cm comma cn tilde to be iota h cross delta mn.
Yes, it will give the same result. So you might be led to believe that, okay, we have done things correctly.
Yeah.
But you see that if we do what Harshit suggested, right?
Yes.
Suggest when you integrate by parts, put it on this side.
Yeah.
The
Yeah.
momentum definition will have a 2.
Yes.
And the commutator now will have an extra factor of half. Right? Because the momentum will be 2Cn, right? The momentum conjugate to Bn will be 2Cn.
Yes.
Okay. So now the BnCn commutator will be half I instead of half I delta mn instead of I delta mn.
Okay.
Right? Because it will be Bm with 2Cn as IH by delta mn, right?
So it will be inconsistent, like.
Yeah, it will be inconsistent with this one.
Okay.
Okay. But as I said, if you go through Dirac procedure carefully, then you will never encounter inconsistencies of this kind.
All right.
Okay. Are there other questions? Is it clear to everybody that there's an inconsistency if you do it two different ways? Okay. What Kaustu was suggesting is that we just use this commutation relation is also consistent with this one, right? So why not say that, okay, this is the correct commutation relation and proceed? On the other hand, what Harshit is suggesting is that you integrate by parts, okay, by adding a total derivative, and then define the conjugate momentum and get the commutator. Okay, that will give an extra factor of half here. Okay, so obviously one of the procedures can be correct at most. Right? Maybe neither are correct, but both cannot be correct. Any questions? Sayan, any question?
No, sir.
Sinjini?
No, sir.
Okay, so let me proceed. Okay. So to proceed, what we will do, okay, just to make the notation a little easier, that we will restrict to some particular n because the variables for different n commute anyway. Okay. Because if you look at this Lagrangian, right, it's basically a sum of different n's, right? There's no cross term between, say, Cn and Bn anywhere, right? Or its derivatives. So clearly, when you quantize this, right, the variables for different n's will come, right? They are completely independent of each other. They react on product Hilbert spaces. So for this reason, we will restrict to some particular n and then proceed to follow Dirac's procedure. So after restricting to some particular n, we see that there are two constants. One is b tilde n minus h bar Cn equal to 0. That we will call chi1. So we will define chi1 as b tilde n minus h bar Cn. And similarly, we will define chi2, where is chi2 as c tilde n plus h bar bn. That's the second constant. So in terms of these, the constants are chi1 equal to 0 and chi2 equal to 0. Okay. So we'll leave it at this stage for now. Okay. And in the next slide, I'll begin by reviewing Dirac's procedure. Okay, I'll give the general procedure that Dirac laid out for quantizing constant systems of this type. Okay. And then once you understand the procedure, then we'll apply it to our system. Okay, so we'll consider a general case. So let's suppose that you have a system with coordinates q1 to qk, these coordinates may not be particle coordinates, they're generalized coordinates. Okay, it could be like our BNs. And conjugate momenta, which are denoted by P1 to Pk. And suppose further that we have m constants, which I'll write as chi1 equal to 0, chi2 equal to 0, chi up to chi m equal to 0. So this vector q basically means that it can depend on all the q's, okay, and all the p's. Okay, so you are not assuming anything about how the constants look. General set of constants, okay, which I call chi1 to chi m. So now, what Dirac says that the first thing you should do is to define this matrix M alpha beta, which is simply the Poisson bracket of the constants. So take a chi alpha and chi beta, any pair, and calculate that Poisson bracket. So what is Poisson bracket? This is the standard definition of Poisson bracket. Yeah, I'm assuming this is familiar to all of you. Okay. In Hamiltonian dynamics, this is how we define Poisson bracket. And sum runs over I equal to 1 to k because there are k coordinates and k momenta. So PB, this subscript will stand for Poisson bracket. And alpha beta here runs from 1 to m. So now, if it so happens that the determinant of this matrix is not identically 0, then the constants are called the second class constants. And this is the case that will be relevant for us, and we'll proceed with this case. When you have first class constants, okay, which means when determinant of m is 0, then the procedure is more complicated. But Dirac has laid down the procedure for that case as well. But let's proceed by assuming the determinant m is not 0. Okay, so that constants are second class constants. So in this case, given any pair of functions f and g of the q's and p's, we'll define the Dirac bracket as follows. So the definition of the Dirac bracket between two functions f and g is that it's, first of all, you calculate the Poisson bracket of f and g, and then there is this complicated expression where you sum over alpha and beta all the way from 1 to m, get the number of constants, and then whatever is in the summand, okay, is constructed out of the Poisson brackets. This is the Poisson bracket of f with chi alpha. Then the M inverse is the matrix inverse of f, right? So you think of this as a matrix, and because the determinant is non-zero, it has an inverse. Okay, that's the matrix M inverse. And then you have the Poisson bracket of chi beta with g. So is this definition clear? Any question?
Sir, why beta must be less than m in that m alpha beta case?
Oh, because there are only m constants, right? See, chi, the index of chi goes up to m only.
Oh, okay.
Right? So you take all the constants and calculate the arbitrary Poisson bracket. Right? That's why alpha beta runs from 1 to m. Is that okay?
Yes.
Sir,
Yes.
sir, we need to do this because our P's and Q's they are not reduced to the minimum number of independent coordinate and momenta. Is it?
Exactly. That's right. So if the Q's and P's had been all independent, right? That means if there is no constraint, then you don't need to do this. Okay. In fact, then the Dirac bracket and Poisson brackets will agree, right? Because this sum will be 0, right? No constant,
Yes.
m is 0, right?
Yes.
So Dirac bracket and Poisson bracket will agree.
Okay. Thank you.
So we need to do this when there are constants, so that the actual number of independent variables is less than 2k, right? Because total number of q's and p's is 2k. But if there are m constants, then the number of independent variables is really 2k minus m. Okay, and the idea is that we want to understand what is the commutator of those 2k minus m variables, right? Because those are the basic degrees of freedom of the system. And in terms of those commutators, you can then calculate other commutators. Is this okay?
Yes.
Okay. Now, one point to notice here is that like Poisson bracket, Dirac bracket is also antisymmetric under FG exchange. Okay, it may not be completely apparent, but let me go through it. So Poisson bracket is antisymmetric under FG exchange. Right? That's clear, right? Because if you look at this, let's look at chi alpha, chi beta. If we had exchanged chi alpha and chi beta, right, you will get del chi beta, del qi, del chi alpha, del pi, right? That's this term, right? And there's a minus sign. Okay? So if we exchange chi alpha and chi beta, that basically exchanges these two terms, which gives a total minus sign. Okay? So this is obviously antisymmetric under the exchange of f and g. Here, what happens is that this one is antisymmetric under the exchange of f and chi alpha. This is antisymmetric under the exchange of g and chi beta. Right? So I could have written this as chi alpha f, and I could have written this as g chi beta. And then because alpha and beta are summation variables anyway, right? We could have relabeled alpha as beta and beta as alpha. To write this as chi beta f and g chi alpha, right? So that basically exchanges f and g. But what it does at the same time is that it exchanges the indices alpha beta here. Okay, because we are relabeling alpha as beta and beta as alpha, so we have to do it everywhere, right? So net effect of this is that net effect of FG exchange is that this alpha beta indices get exchanged. It becomes beta alpha. But now, if from the definition of M, you see that M is an antisymmetric matrix, right? Because this is antisymmetric under the exchange of alpha and beta. And the inverse of an antisymmetric matrix is also antisymmetric. So M inverse is also antisymmetric under the exchange of alpha and beta. So M inverse beta alpha is really minus M inverse alpha beta, which basically shows that the second term is also antisymmetric under the exchange of f and g. So the first term is antisymmetric under the exchange of f and g. The second term is antisymmetric under the exchange of f and g. And as a result, the Dirac bracket is also antisymmetric under the exchange of f and g. Okay, so that property is the same as that one Poisson bracket. Is this argument clear? Ayan Patra, is it clear?
Yes, sir.
Ayan Sahu?
Yes, sir. It's clear.
Okay. So I'll proceed. Anybody else has any question, comments? Okay. So now let me give Dirac's procedure for quantization. Right. So far you have defined the Dirac bracket. So now what Dirac's procedure says is that you take these Qi's and Pi's, so you know that they are not independent. So you choose a set of 2k minus m independent variables. So it could be all the Qi's and some of the Pi's, or all the Pi's, some of the Qi's, or some Qi, some Pi, or some linear combinations of them. Doesn't matter. You take a set of 2k minus m independent variables, and let's call them capital Q1 to capital Q2k minus m. So now, given this, we calculate the Dirac bracket of QA with QB. Okay, and you do this for all A and B between 1 and 2k minus m. And let's suppose that the result of calculating this Dirac bracket is given by WAB. Now, the procedure for quantization is that we will regard QAs as operators. Okay, that's what you do normally when you go from classical to quantum mechanics. You regard the coordinates and moment as operators, so you regard the QAs as operators. But the commutation relation that you propose is that the commutator of QA and QB is given by IH bar WAB. And you do this for all A and B between 1 and 2k minus m. Now you notice that if the Dirac bracket and Poisson brackets are the same, okay, namely if there are no constraints, then this gives the standard quantization procedure. Because what is the standard quantization procedure? If you take a Poisson bracket, right, between the Q's and P's, where QP Poisson bracket is 1. And then you replace it by saying that 1 over IH bar times commutator bracket is 1. Right? or the commutator bracket is I h bar times whatever the Poisson bracket was earlier. Here, what we are saying is that we do similar thing, except that this commutator bracket, instead of setting to I h bar times what the Poisson bracket was earlier, we set it to I h bar times what the Dirac bracket was earlier. Okay, because WAB is the Dirac bracket between Q and Q. Is this clear? And the main advantage of this is you can show that this procedure is independent of how you choose the variables Q and Q. Or how you choose the Lagrangian. If you add total derivatives to Lagrangian, you get the same result at the end. So in that sense, this procedure is robust. Whereas if you just try to guess what the commutation relation should be by trying to simplify the Lagrangian, sometimes you may make errors.
So this WAB is also an operator, right?
Yeah, it's an operator, but in simple cases that will be of relevance to us. This will be a C number.
Okay.
Okay, but in general, yes, this could be operators.
Also, does this Dirac bracket satisfy the Jacobi identity?
Yes, it does.
Okay.
Okay, otherwise it would be inconsistent to replace this by commutator bracket, right?
Yeah.
Because commutator bracket certainly does satisfy Jacobi identity.
Hmm.
So this is only the result. But if you want the full details, okay, the one place where you can look up is Dirac's book. This is not the standard quantum mechanics book of Dirac, but he has another book called Lectures in Quantum Mechanics, and this has 4 lectures, of which lecture 1 basically is devoted to quantizing constant systems. Okay, are there questions? Aparajita, is it okay?
Yes, sir.
Sukalpa?
Yes, sir, it is okay.
Okay, so what I'll do now is to proceed and apply this procedure to the case at hand. Okay, the quantization, that the system that you want to quantize. Okay, so let's recall that in our case, we have 2 constants, chi1, which is b tilde n minus h bar cn, and chi2, which is c tilde n plus h bar pn. So let's first calculate the Poisson brackets of these constants. Now, of course, chi1 Poisson bracket will be 0, chi2 Poisson bracket will be 0, right? Because it's antisymmetric. Chi1 Poisson bracket, let's see. So there is a b tilde n with h bar pn, right? So this is momentum that's coordinate. So that gives 1, right? So that gives you, gives minus 1, because momentum coordinate Poisson bracket is minus 1. So that's minus h bar. And then you have another term which is minus h bar times cn with cn tilde. That's another minus h bar. So chi1 chi2 Poisson bracket gives you minus 2h bar. And the chi2 chi1 Poisson bracket by antisymmetry is just the negative of this, so it gives 2h bar. So this, with the help of these equations, we cannot generate the matrix M, right? Because you remember the M alpha beta was the chi alpha chi beta Poisson bracket. So the diagonal entries are 0, and the off diagonal entries, okay, this is M12 because that's chi1 chi2 Poisson bracket is minus 2h bar, and this is M21, the chi2 chi1 Poisson bracket. And as you can see that M is antisymmetric matrix. It has non-zero determinant, obviously. So you can compute M inverse, okay, and that's given here. Okay, you can easily check that M inverse M is 1. So our goal will be to calculate the Dirac bracket of Bn and Cn, okay, because we will eventually want to take Bn and Cn as independent variables. There are 2 independent variables because there are 4 variables to begin with: Bn, Cn, b tilde n, c tilde n, and 2 constants. So there are 2 independent variables, and we will choose them to be Bn and Cn. So then, to compute the Dirac bracket of Bn and Cn, what we need are the commutator, are the Poisson brackets of Bn's with the constants and the Cn's with the constants. And here I have written down the result. So let's check Bn with chi1. Right? Chi1 has a Bn tilde. Right? That's the term which gets non-zero Poisson bracket with Bn, right? With the conjugate momentum. So that gives you 1, right? Bn with Cn, of course, gives you 0. Both are coordinates. Chi1 with Bn is the negative of that, so that's -1. Bn with chi2, you can see, is 0. Right? Because Cn tilde, Bn with Cn tilde, of course, is 0 because this is the conjugate momentum to Cn, not to Bn. And Bn with Bn obviously is 0. Okay, so Bn with chi2 is 0. Similarly, chi2 with Bn is also 0. Now, if you turn to Cn, Cn on the other hand has no Poisson bracket with chi1, right? Because it doesn't have a momentum conjugate to Cn in the expression for chi1. So Cn with chi1 is 0, chi1 with Cn is 0. Cn with chi2 has a non-zero Poisson bracket, right? Because there is a momentum C tilde and sitting here. So that's 1. And chi2 with Cn gives you -1. Any questions? Is it okay so far? Okay, so let's now use this to compute the Dirac bracket of Bn and Cn. Okay, so the Dirac bracket between Bn and Cn, let's look at the definition. That first you have to compute the Poisson bracket between Bn and Cn. That's of course 0, right? Because these are both coordinates to begin with. Then we have Bn chi alpha, okay, but only the alpha equal to 1 term contributes, because you can see from here that chi2 with Bn gives you 0, so only the alpha equal to 1 term contributes here. So Bn with chi1. Similarly, here you had a chi beta with Cn, but only the beta equal to 2 term contributes, right? Because only the chi2 has non-zero Poisson bracket with Cn, chi1 Poisson bracket with Cn gives you 0. So that fixes this to be chi1, this to be chi2, and that in turn means that the component of M inverse that we are looking for is the 1, 2 component, right? Because 1 contracts with 1, 2 contracts with 2. So that gives you, this is 1, okay, from here. This M inverse 1, 2, that's 1 over 2 h bar, right? And then chi2 with Cn gives you -1. So that's 1 over 2 h bar. So Bn Cn Dirac bracket is 1 over 2 h bar. So then the rule of quantization is to replace the Dirac bracket by 1 over I h bar times commutator bracket, right? Keeping the right hand side the same.
Sir,
Yes, go ahead.
yeah. M inverse alpha beta, there is alpha beta sum. So M inverse, why not 2, 1? Because
Yes. The point is, if you go back, go to the definition. There is sum over alpha and beta, right?
yeah,
So this index alpha has to match this index alpha.
yeah,
And what you saw is that only alpha equal to 1 term contributes here, right?
yeah.
If
Okay,
alpha
okay,
of 2, it will be 0.
okay.
Right? That's why the other components of M inverse doesn't contribute.
Okay.
Is that okay?
Yeah.
Sir,
Yes.
you have an extra H cross in those Poisson brackets.
Extra H cross.
Yeah, you have just written 1, but that let's say Cn2 and chi, Cn and chi2, that should be H cross. If you see.
Okay, Cn with chi.
No.
No. Cn with chi2. Cn with chi2 is not H bar because Cn with Cn tilde, right?
Yeah.
Right? So Cn with Cn tilde, the Poisson bracket is 1. See, this H bar doesn't enter, right?
Oh, yes.
Yeah. If you had a C tilde n, then there is H bar will enter, right? But because we have independent variables, so Bn and Cn, these brackets do not involve H bar, right? Because only these B tilde n and C tilde n are relevant part of chi2 that appears here, right? In these two lines.
Okay.
Is this okay?
Yeah, but then when we divide it by 1 over IH cross, oh, Okay.
4.
Okay.
So this is the
So-
rule, right?
Okay.
Because
Okay.
I said the commutator bracket should be IH bar times the Dirac bracket, right?
Okay.
So that's why,
Yes.
but that's another way of saying this is that whatever Dirac bracket relation we had, right? We'll replace the Dirac bracket by 1 over IH bar times commutator bracket.
Okay.
Okay. So in other words, let's go back to Dirac's procedure. I have just taken the 1 over IH bar on this side. Right? That if QA QB was WAB, right? The rule for quantization is 1 over IH bar times QA QB, commutator bracket is WAB. Is that clear?
Yes, sir.
Is this clear to everybody?
Sir, why you choose Bn and Cn as independent variables? Can we choose Bn and Bn delta as independent variables?
Yes, we can. We can choose any two independent variables, right? And that's the main advantage of Dirac's procedure, that whatever variables you choose, right? You can choose Bn and Bn tilde, you can do it yourself, right? Or Cn and Cn tilde, or Bn and Cn tilde. Well, Bn and Cn tilde is probably not good because those are not independent, right?
Yes.
Okay, you pick any pair of independent variables from here and carry out this procedure. The end result will be the same. Is this clear?
Yes.
Okay, well, it's clear, meaning the statement should be clear. It's of course not clear from whatever I have said, right? I mean, if you do it with other variables, you will find that the final result will not change. Okay. Whereas if you didn't follow Dirac's procedure, then the confusion that arose earlier, right? Because Harshit had suggested one way of doing it, Kaustubh had suggested another way of doing it. Right? Let me go back to here. Not here in this. So Harshit had suggested that let's do integration by parts. Okay, by thinking of this as a part of the action. Then define the conjugate momentum. And then think of Bn and Cn as independent variables. Whereas what Kaustubh was suggesting, that we use this anyway to get this. And then this is consistent with the second one. Okay, so why not use this? But that would be inconsistent with what Harshit was suggesting, okay, because that will have a factor of I by 2. But that would have given the right answer. Okay. This gives you I delta Mn. Okay. If what Harshit was suggesting is done, okay, that will give you the same commutator as I by 2 delta Mn. Okay. And what we see by following Dirac's procedure, which is here, is indeed that I by 2 is the right answer. Okay, BNCN commutator is I by 2. Is this clear?
How do you know the Dirac procedure gives us correct result?
How do I know that?
Dirac's procedure gives us correct result.
Yes. So that for that you have to read Dirac's lectures. Okay, because he outlined the whole procedure, right? This lecture 1, if you read, because what I have done here is that I have not explained where this procedure comes from, right? What I have done is that I have just given the algorithm, okay, what Dirac gave. But if you want to understand where it comes from, okay, just look up this lecture. Okay, it's a short lecture. It's readable with the standard knowledge of quantum mechanics. And there, of course, you will find more, because here he also discusses how to quantize in presence of first class constraints. Okay, when determinative aim is 0. Okay, I have just picked the case of second class constraint because that's what we need for the present problem. Is this okay?
So in these two ways, once when we were taking the integration part by parts, and the second, in both these ways the Hamiltonian is the same.
Yes, the Hamiltonian will be the same. Yes, indeed. So the Hamiltonian doesn't change. This procedure doesn't affect construction of the Hamiltonian, but what it affects is the construction of the actual quantization.
Okay.
Is this okay? Okay, Priya, you had question?
Yes, sir, it is okay.
Okay. Anybody else has any question? Harshit, is it okay?
Sir, I have a question. In this process, the constraint that we are getting is solely from the Lagrangian. The Lagrangian contains all the information about the constraints, right? But it could be the case that the Lagrangian does not have any information about the constraint. Let's say the particle is on the surface of a sphere, and we are writing the Lagrangian in Cartesian coordinates.
Okay.
So we'll have to put that the particle is on the sphere is a constraint that is not present in the Lagrangian.
Okay. Okay.
And we'll have to put it by itself. Put it by ourselves.
Okay.
So will it work there?
Yes. So the point is, it will work there, but the point is here that those constants are in fact somewhat trivial, because those constants you can think of just as constants on the coordinates, right?
When
we
we are writing
y square plus z square equal to a square, right? So you could just eliminate z from the beginning.
Okay. But if I were to work with the XYZ coordinates, I would not be changing the coordinate system itself. What I'm saying is you view the constraint as differentiated. X square plus y square plus z square is r square. So you can differentiate it. X dot plus y dot plus z dot equals 0. And I can write this constraint in terms of x and p's. Once I find the momenta from the Lagrangian. So it will be x px plus y py plus z pz equals 0.
Yes.
And that will be a constraint.
Yes.
That does not derive from Lagrangian.
That is true. So there will be two constants, right? X square plus y square plus z square equal to a square, and xpx plus ypy plus zpz equal to 0. Right? Yeah, and you can use this procedure for quantizing that system.
Okay.
Yeah. But in that case, it's much easier to just eliminate one variable.
Yeah.
Yeah. But you could use this procedure there also.
Okay.
Other questions?
Sir, I had a different thing. Like right now, we are just considering the Lagrangian for what would give us the classical, the Schrodinger equation.
Yes.
In principle, we can write, like we should be able to write a Lagrangian for all equations.
Yes.
But not all of them will have a linear in time derivative. Like Dirac equation does have, but
yes.
But if in other, maybe in, I'm not sure what the Lagrangian for Klein-Gordon is, but maybe it does not have a single time derivative.
Yes. In that case, there is no constraint, right? You can proceed with Poisson bracket instead of Dirac bracket.
Yeah, but and in the end, the Hamiltonian expression will also not be something like A star A. Will it be?
Well, it will be eventually. You will see.
Okay.
Okay, you have to do some work, but it will be something like that. Okay, you have to introduce A and A star appropriately.
All right. Okay.
Okay, other questions? Okay, so let's then proceed. So we have got this. Okay, so here what I have done is that I have just used the fact that for m not equal to n, all the commutators are 0 anyway. So I wrote it this way. Okay, that when n is not equal to m, I have delta m. Okay? This I by 2 is the important part. Okay, so here are the commutators again. Okay. And now let's verify that it gives us back the commutator that we had used by thinking of the psi and psi star as independent variables, or A and A star as independent variables. Okay. So for that we go back to our definitions of AMs and AM daggers instead of B and C. So from this we can see that AM AN commutator, okay, which is given here, actually gives you 0 because of the fact that you see that BM BN of course have 0 commutators, CM CN has 0 commutator. So there are two terms. One is I times BM commutator CN, that's here, and the other one is I times Cm commutator Bn. But of course, this is negative of this, right? This is I times half delta Mn. This is I times minus half delta Mn. Okay, so that gives you 0. Similarly, you can compute other commutators, and what we get at the end is Am, An dagger. This is the only non-zero commutator. In fact, you can see why, right? Because the difference between Am, An and Am, An dagger is that there's a minus sign here, right? And because of this minus sign, this sign changes to minus sign. So now the two terms, instead of cancelling, add. Okay, and you get Am, An dagger is equal to delta N. In fact, you'll get the minus sign in front of this, not here. Okay, because this is the term that here you'll get minus sign. So DMCN commutator will have extra minus sign. Okay, and that gives you half from here, and that's total delta M. Is this clear?
Sir?
Yes.
Can this be used as a consistency check? Like suppose we did this and we work backwards from this relationship and calculate this, and then we take Dirac's procedure and do this.
Yes, it can, provided you trust this. See, the way we got this result, right? Was by
Yes.
thinking of the psi and psi star as independent variable, okay, and dealing with the constant in a particular way, right? You just said that you set the conjugate momentum to psi of psi star to 0, right? And then eliminate the psi dot or psi in terms of the conjugate momentum to psi, right? Psi dagger in terms of the conjugate momentum to psi, right? But
Yes.
you can ask that how do you know that's the correct procedure, right? But that's why we started, right? Because last time, if you remember, that there are some worries that we are using complex Lagrangian and complex variables, right? But how do you know that you can really treat psi and psi dagger as independent variables? Okay, here there is no confusion, right? Because the Dirac's procedure tells us what to do, okay, for any kind of constraints. Okay, we have followed it and we have arrived at this. So in a sense, you can say that it's a consistency check for the procedure that we carried out last time. Okay, not the other way around.
Okay.
In a sense, Dirac's procedure is the more fundamental because that gives a result in all cases. And as a special case, we get this.
Okay, sir.
Other questions? Anand, is it okay?
Okay, sir.
Tanay,
Okay, sir. It's fine.
is it okay? Okay, let me proceed. So now let's look at the expression for the Hamiltonian. So what was Hamiltonian? We had gotten the expression for the Hamiltonian earlier, right? En times Bn square plus Cn square. Let's see. This is a classical Hamiltonian, but of course you can, yeah, here, right? We now think of Bn's and Cn's as quantum operators. So all you have to do is that I have to substitute Bn in terms of An plus An dagger. Okay, so Bn from here is An plus An dagger by 2, right? That gives us 1/4. And Cn is I times An minus An dagger by 2, right? So that gives you this minus sign because I square is minus 1. So this is what we get. We expand out the squares, taking care that An dagger is different from An dagger N. Okay, the An square cancels, An dagger square cancel. What you end up with is with this. This you would recognize as the harmonic oscillator Hamiltonian. But like what we did earlier, I'll rewrite this as this An dagger as An dagger N plus half, and that half is just a constant term that I'll just write, right? Because as we said, we are really interested in measuring differences in energies. An overall constant added to the energy has no effect, so we'll just write a constant term. and then this becomes the same as what we have found out. So you have recovered the correct commutation relation and the correct Hamiltonian. And that means that you have also recovered the correct commutation relation between the size, because that was obtained just from the commutation relation between the ANs. So let me remind you that after you substitute psi, and similarly for psi dagger as AN dagger times UN star, we got these commutation relations, right? Psi dagger is delta cube r minus r prime, and psi commutator is 0, psi dagger is 0. That still holds simply because these commutation relations are the same as what we had found last time. Is this clear?
Clear, sir.
Okay. So what we are going to do now is to go back on track. So this is where we are arrived at last time. Okay. Write the Hamiltonian, write psi, everything in terms of psi. What we will do now is to find representation of the various other operators in the third description. Third description, let me remind you, is where you think of the psi and psi dagger as the independent variables. So you want to express, for example, various other operators. Right? You already know the Hilbert space states map into each other. Hamiltonians match. But you want to know in general, how do the other operators map in this third description. So for this, let's go back to the kind of operators that we dealt with. So let's start with one body operator. So let me remind you the definition of one body operator. One body operators are sum of terms. Okay, it of course has to be completely symmetrized under the exchange of the particles. But it has the property that each term involves the coordinates and momentum of one particle. Yeah, that's what we call b hat term, right? This involves the coordinates and momentum of the ith particle. And we have already worked out in the second description, okay, in terms of the harmonic oscillators, what the corresponding operator is. Right? So the b hat, okay, that's the image of this b hat n in the harmonic oscillator description, is given by this. And p and p's are just constants, okay, given here. Here R1 is just a dummy label, right? You could have replaced it by just dq bar. But it simply represents the matrix element of this one body operator b hat 1 between the two eigensets of the Hamiltonian, up and UN star. So the idea now is that we are going to substitute this b expression for b and p here and try to write the resulting expression in terms of psi and psi dagger. Okay, because we know the relation between the ANs and the psis, right? We know the relation between the ANs and the psis because that's given here. Right? And similar relation between AN daggers and the psi daggers. So let's see what we get. Okay, so here is the expression for b hat. Okay, but now b and p we have substituted in terms of the matrix element explicitly. So that's here, right? This is our b and p, and we have the a and p dagger AP. Okay, now we are going to move things around a little bit. So for this, we note that these are operators, N, dagger and AP. These are operators, but these are operators in the Hilbert space of the second quantized theory. Right? These are operators in the Hilbert space that is built out of the harmonic oscillators. Okay, by the creation of operators of the harmonic oscillator. So these are on the other numbers. Right? As far as that Hilbert space is concerned, these are just C numbers. Right? B hat 1 is an operator, but it's just a differential operator. Right? It doesn't act on the Hilbert space of states. Right? It's just think of this as a differential operator. So this quantity, integral dq r1, right? I mean, all the things which are involved in this integral are just C numbers from the perspective of the Hilbert space. Okay, because it doesn't act on the Hilbert space. And for this reason, I can just move this AN dagger, which is here, all the way here. It makes no difference. But once you do it, then you see that UN star R1, AN dagger T, from here, is the psi dagger of TR1. Right? UN star R1 AN dagger T is psi dagger of TR1. So once we move the AN dagger here, I can combine this AN dagger of UN star to write this as psi dagger, and I can combine this AP with UP to write this as psi. So what we get as the representation of the operator B hat in the third description is integral d cube R1 psi dagger B hat 1 psi. Is this clear to everybody? Any question? Renu, is it okay? Jisun?
Yes, sir.
It's fine? Okay.
Yes, sir.
Okay. Saptarshi?
Yes, sir.
Okay. Can I proceed? Okay. So now, if you look at this expression, right, you see that it has a nice interpretation. But after all, let's imagine that this was just ordinary wave function, right? Let's forget about the operator interpretation. Suppose this was an ordinary wave function. Then what does it represent? This represents a matrix, the expectation value of the operator B hat for one particle states, right? Because integral psi star B hat psi, right? This R1 of course is an integration variable, so it doesn't matter whether you write R1 or R. So integral psi star B hat psi is just the expectation value of the operator B hat. So this gives a simple algorithm for translating one body operators to the third description directly. And the algorithm says the following: that you take the expectation value of the one body operator in the single particle wave function psi of TR1. And whatever expression you get, which is here, we regard psi and psi dagger as operators instead of as just wave functions. So that's the procedure for translating the one body operators to translating one body operators to the second quantized description.
Sir,
Yes.
can we think of this psi star or psi at one point as eigenvalue of this psi dagger operator or psi operator, the wave function?
Well, it's not quite the eigenvalue, right? You are thinking of the position space representation somehow, right?
Yes, yes.
Yeah, we'll try to see next time, right? To what extent we can work with the position space representation, but it's not quite the eigenvalue.
Okay.
Okay, but
because this psi dagger and psi are acting on some Hilbert space. So, so psi dagger is complex operator, but I mean some eigenvalue or eigenvector. That notion, is it there or?
Well, the point is the position. If you take the position eigenstate, right?
Yes.
Instead of building the multi-particle states in terms of energy eigenstates, you are done it in terms of position eigenstates. Okay. Then you could think of the psi RT1, the wave function of the position as some of the eigenvalue of the operator psi dagger, but it's not very concrete because of this fact that position eigenstates, as you know, are not normalizable, right?
Okay.
Right. So one has to be more careful. So let's not think of it that way, right? Next time we will see how to deal with this system directly in the position space without having to go to the energy eigenstates.
Okay. Okay.
Okay. Is this okay?
Yes.
Okay. So just
hello, sir.
Yes. Go ahead, please.
Sir, we are doing like operator in a quantized field, representing of operator in a quantized field.
Yes.
We are doing.
Yes.
Sir, it's my doubt, sir.
Pardon?
Hello.
I didn't hear the last question, last word. Can you say it again?
Sir, I'm saying that is it a representation of like operators in a quantized field?
No, the fields themselves are quantized because the psi was a field to be a classical field to begin with. Now we are taking up the size as operators.
Okay. So
Right?
yes, sir, yes, sir.
Psi as operator, I mean, and you can see it from here, right? If you look at this expression over here, right? UNs are functions. These are just numbers, right? Given an R, UN of R is just a number. But AN of T is an operator, right? So that makes psi as an operator. So these are operators. The fields have become now operators acting on a Hilbert space. If you have difficulty in visualizing fields as operators, right, you can always go back to an expansion of this kind and regard the ANs as operators. Right? These are not difficult because this is harmonic oscillator TS and annihilation operators. But once you write psi TR as a linear combination of operators of this kind, right, then it's clear that psi itself is an operator. Right? Because linear combinations of operators are also operators. And you can see it from here, right? The commutator between psi and psi dagger is not zero.
Okay, sir. Okay, sir.
Is this clear?
Thank you, sir. Yes, sir.
Are there other questions? Okay. So let me discuss. Yes, go ahead, please.
So, sir, the inner product of R and T are the position bra, and the psi dagger RT and the vacuum state, that will give the wave function, right? Like psi dagger RT acting on vacuum and taking that inner product with position bra, that will give the wave function
Well, that
value.
will give you the delta function, right? Because basically this psi dagger RT acting on a vacuum, right?
Yes.
What it does roughly, okay, again, don't take it too seriously, but what it does roughly, that it creates a state in position eigenstate R prime. Is that statement clear? This psi TR dagger operator, right?
Yes.
Okay. So let's do a T equal to 0. Okay, because maybe I should emphasize it at this point itself. Okay, that so far the way we have been setting up the problem that I am using the Heisenberg picture, where all the operators have time dependence, but the states, the Hilbert space states that we are creating, they are created at T equal to 0 once and for all. Right? So the states do not have time dependence, right? So when I write AN dagger on the vacuum, right, that is really done at T equal to 0. So let's do that. So let's apply psi 0 R dagger or psi 0 R prime dagger acting on the vacuum. So roughly what it is doing is that it is creating a state in position eigenstate R prime. Just like AN dagger on vacuum will create a state in energy eigenstate with energy eigenvalue En. Is that clear?
Yes, sir. Yes. And then if we take the inner product with the position space, then that will give the function as psi R prime. Is it like that?
You take the inner product. Okay. See, suppose you create by psi T R prime dagger on vacuum, right?
Yes.
That gives a position eigenstate R prime. Okay.
Okay.
Then
it becomes.
Suppose you want to take the inner product with an energy eigenstate. Okay. So what are energy eigenstate? They are created by AN dagger on vacuum.
Yes. Yes.
So now suppose you want to calculate the inner product. So on one side you have vacuum AN.
So we have to expand that position in the energy eigenbasis.
Exactly. You have to expand the position in the energy eigenbasis, right? And what we will get is even of R prime.
Okay.
That's what we expect, right? If you create a state in position eigenstate R prime, and if you take the inner product of that with the energy eigenstate En, right?
Yes, yes.
The result should be UN of R prime, right?
Yes.
Yeah, and that's what.
So, okay. So does it mean, sir, like creating a particle in a particular position? So then we will have all those n components for those energy eigenbasis. and then does it mean that creating lots of particles in different energy levels?
No. The point is, if you apply psi dagger once, you create only one particle. You may create linear combinations of many particles, many one particle states, right? Because psi dagger acting on the vacuum will be linear combinations of n dagger acting on vacuum, right?
Yes.
N dagger acting on vacuum is always a one particle state.
Okay.
Right? You can change n.
So that will be superposition of different energy, single particle energy basis.
Exactly. If you want to create two particles, right? Suppose you want to create two particles, one at position r, one at position r prime. Then you have to apply psi dagger t r prime, psi dagger t r.
Yes.
Is that clear?
Yes, sir. Yes.
That times the energy will be energy of these two particles will be same. Energy eigenstate.
Energy of the two particles. Which two particles?
That what you have said now, that r and r prime at the position.
No, they will not be the same. So, okay, the position eigenstates have infinite energy, right? So you can say they are the same, but they are infinite. See, if you create a particle in the position eigenstate, right? Because of the momentum uncertainty becoming infinite, we know that the particle has infinite energy.
Okay.
So once you have created a particle in the position eigenstate, you cannot talk about its energy anymore, right?
Yes, sir.
What you can do is that you can talk about its overlap with an energy eigenstate. That's finite and that's given by this event.
Okay.
Is this point clear?
Yes, sir.
Is it not clear to anybody? Please ask. Okay, so let me give a simple example of this, which is the number operator. The number operator is just a n dagger n, and when you express it in terms of the okay, m dagger n, but that you can write in this way, right? Because this is just delta mn, this is orthonormality of wave functions, and that gives you integral dq bar times psi dagger psi. And again, you can see that this is quite natural. Because after all, what does in a one particle quantum mechanics, right? What does psi star psi do? It gives the probability of finding a particle at a given point, right? When you think of this as an operator, what it gives is not the probability of finding a particle at a given point, but the number density of particles at a given point. Because you can have multi-particle state, right? This is defined in a Hilbert space, which can have arbitrary number of particles. So when you think of this as a second quantized operator, psi dagger psi has the interpretation of a number density of particles at the position r. That's an operator, of course. The integral of this is a number operator. That's the total number of operators, total number of particles that you have in the system. And in the same spirit, the Hamiltonian is given by this, right? You calculate the expectation value of the one particle Hamiltonian in psi, and then make this into operators.
Sir, how can you write in the number operator expression second section to third expression?
This one? Oh, because this is you use an orthonormal, right?
Okay.
This is delta mn, right? So only
Yes,
the n term will contribute. So that's what I have done, and then I have combined am dagger with em star and an with even. Other questions?
Sir, and the small h hat, it will act on the un part of this psi.
Exactly.
The position.
Exactly.
Okay.
So what you mean by small h hat on psi, right? If you expand psi in terms of a and t even of r, right? Small h hat will act on the even part of this.
Yes. Okay.
Is this clear to everybody? Because these operators, right? These one body operators that we have introduced, right? This b hat in general, they act on only the u part of it, right? Because a is an operator in a different Hilbert space, and they commute with this b hat part, and h hat is just a special case of that.
So can you repeat once more?
Yes. So the question was that let's take this Hamiltonian here, right? What does this mean, right? If you want to make sense of this, that the easiest way to make sense of this is you just expand psi in this basis. Okay, small h hat is just think of it as a differential operator minus h bar square by 2m times del square plus the potential, and that differential operator commutes with n altogether, right? Because n, as far as the differential operator is concerned, it just commutes with it, right? This is an operator in a Hilbert space, but it's not a differential operator, right? It doesn't have any art dependence. So when you talk about h hat on psi, right, h hat really acts on even. Right? That's the reason why here, for example, right, I could take the n dagger on this side, right? Because this b hat 1 has nothing to do with the n dagger, right? N dagger is an operator in a Hilbert space, where these are just differential operators acting on functions.
Yes, sir. Yes, sir.
Is that clear?
Yes, sir.
Okay, so let me now give the expression for the two-body operator, and then I'll stop for today. So let me remind you that the two-body operator v hat n was given by this. This was in the first description as multi-particle system, and we have taken this v hat ij to be symmetric, and I also restricted the sum to I not equal to j, okay, because I equal to j term is really a one-body operator. And what we have seen is in the second description, in terms of harmonic oscillator, this v hat n gets mapped to this operator v hat, which is given here, and Vmn pq again is given by an integral of this form. This is just a set of numbers, right? Because once you evaluate the integral, you just get a set of numbers, because v hat 1 2 is a differential operator that involves the coordinates and momenta of the particle 1 and 2. Now we can easily translate it to the third description. Because all you have to do is that we will have to use this expression for v hat and substitute the expression for Vmn pq that is given here. And that's what I have done here. Okay, this is exactly analogous to what we did for one body operator. Okay, just a more complicated looking expression. But now what we'll do is that I'll bring am dagger here, n dagger here, and then ap here, aq here. Okay, because again v hat 1 2 this as an operator commutes with these objects, right? This is a differential operator acting on space of functions. These are operators acting on the Hilbert space of states. Okay. So if you had to want to commute with these operators, so you can move them around. And what you end up with, okay, by combining am dagger with em star, you get psi m r1 dagger. Okay. Combining n dagger with un star, you get psi m r2 dagger, and so on, psi r2 dagger. So this is the final expression we get. Is this clear? Okay. So for example, if v hat 1 2 is p1.p2, okay, then this v hat 1 2 is just given by this expression over here, right? And as you can see, these are differential operators acting on psi that acts on the coordinate r, okay, but not on the a and t's in the expansion of psi. Okay, that's how you can move the a and around. So again, this can be translated to a simple algorithm, because look at this expression over here, right? What does it say? This can be interpreted, right? Suppose you replace the psi daggers by psi star, go back to the classical expression. Then this can be interpreted as the expectation value of this two-body operator v at 1 2 in a two-particle wave function that's given by psi tr1, psi tr2. So the algorithm then to arrive at an expression like this is that we simply take expectation value of the two-body operator in the two-particle wave function, okay, with the same wave function psi, and then in the resulting expression we simply regard psi dagger operators. And you can check that the same procedure works for k-body interaction. If you have taken a k-body interaction where you have sum over k such indices, okay, vi1 to ik, right, with I1 not equal to I2, I2 not equal to I3, and so on, and then try to translate this to an operator in the third description, all you have to do is that you take this k-body operator, calculate its expectation value in the usual k-particle quantum mechanics in a state that involves product of the size, right? Psi tr1, psi tr2 up to psi trk. Calculate the expectation value, and then at the end of the calculation, we just replace psi as an operator. So psi star will be replaced by psi dagger, and you have to think of psi and psi dagger as operators. So this is the general procedure for how to construct a k-body operator in the second quantized description. Okay, are there questions?
In third description, operator has to be written in terms of psi.
Yes, so third description, size are the independent variables, right? So the operators are written in terms of size. Of course, there afterwards you can write in terms of the A's if you want, right? But the basic variables are psi tr, right? Because it started with the Schrodinger equation and started quantizing it, right? So the variables there are psi and psi star. Okay, so that's what one means by the third description.
So what are the first and,
Pardon?
what are the first and second, third description?
Okay, so the first description is where you just think of this as a multi-particle quantum mechanics. Okay? Just think of this as an n-particle quantum mechanics and write the wave function as a function of R1 to Rn. That's what you normally do if you didn't know about quantum field theory or second quantization, but just doing quantum mechanics. So the second description is where we replace that system by a system of infinite number of harmonic oscillators, but without saying where the harmonic oscillators come from, right? We just made an ad hoc procedure of introducing one harmonic oscillator for every energy eigenstate of the first in the of one particle quantum mechanics, and then wrote down the Hamiltonian for the harmonic oscillator system. So that is the second description. And the third description is where you actually start from the Schrodinger equation and quantize it. But all three, as we know, are equivalent descriptions, right? Because you can take operators in the first description, map it to operator in the second description, and that in turn can be mapped to operators in the third description. Is this clear?
Yes, sir.
Other questions?
Sir,
Yes, go ahead, please.
why an operator which is a function of time is not considered as a differential operator?
Are not considered as? Sorry, I couldn't get your question.
Differential.
Oh, because these operators are like A and daggers, no? A and dagger doesn't have anything to do with R. If you look at this, right? The differential operator is in R, right? So ANs act on a Hilbert space of states,
Yes.
right? That's created by the creation and annihilation operators of the harmonic oscillator t equal to 0. And you pick up the commutators between the ANs and AN daggers in that Hilbert space. But whether you write it as ANT times UNR, right, or UNR times ANT, makes no difference, right? Or ANT times gradient of UNR, or gradient of UNR times ANT, makes no difference. So it is in this sense that ANT commutes with any gradient or any derivative operator on the event.
Okay, sir.
That clear?
Yes.
Actually, UN and AN are different function in different space. That's why.
Exactly. So UN of R are C numbers as far as the Hilbert space is concerned. Right? These are not, you don't think here in terms of UNs as operators, right? These are just functions. So given an R, UN of R is just a number, right? There's no measurement uncertainty of what UN of R is. AN on the other hand is an operator on the Hilbert space. So UNs or any of its derivatives can be moved around anywhere inside the operator algebra. Is this clear?
Yes.
Any other
Sir?
question? Yes.
So instead of introducing one harmonic oscillator for every energy eigenstate, can we introduce a harmonic oscillator for every some other position or momentum eigenstate like that? Is it
Well, you
possible?
could have that in a sense, as I said, those are the side diagrams and sides.
Okay.
But
Oh yes, yes.
you cannot have the usual commutation relation. That's you have to have this delta function commutation, right?
Yes.
That's why using discrete energy levels is easier. Okay, this has happened because the position eigenstates are continuous, right? R is a
Okay.
continuous variable.
Okay. So same thing we can do for any observable like spin. So if there is spin, so we can introduce one harmonic oscillator for every spin state.
Well, see, not every spin state, right? Every state of the first quantized theory, every single part of the first quantized theory, you can introduce a harmonic oscillator.
Oh, okay, okay, okay.
So that's the general.
Okay. Okay.
Okay, so maybe I have to log out because the next class will start on this. So we'll meet tomorrow, and if you have any questions, you can ask tomorrow before the lecture.